Hello and welcome to this lesson on the extraction of metals using the reactivity series and displacement reactions. In today's lesson, we will firstly explain how the reactivity series and displacement reactions are used in the extraction of metals, focusing on the use of reduction with carbon. Then we will also highlight the limitations of using carbon reduction. So far, you've learned about the reactivity series and how displacement reactions can help us determine which metals are more reactive. You've gained a good understanding of how these reactions work and how we can predict the outcomes based on the reactivity of the metals involved. Today's lesson will build on this understanding and examine how such principles are useful in industry. Metals can be divided into three groups in the context of extraction method: metals more reactive than carbon, potassium to aluminium, zinc, iron, and copper, which are less reactive than carbon, and finally, silver, gold, and platinum. The first is extracted by electrolysis, the second by carbon reduction, and the third exists as pure elements. Let us examine each group in more detail. We will start by the second group. Zinc, iron, and copper are less reactive than carbon. You know from previous learnings that a more reactive element can displace a less reactive element from its oxide. This is key to carbon reduction. During carbon reduction, metals are heated with carbon, and the reaction proceeds as follows. Metal oxide plus carbon becomes metal plus carbon oxide, so either carbon monoxide or carbon dioxide. As you can see, the metal oxide loses the oxygen and is reduced. Conversely, the carbon gains the oxygen and is oxidized. For example, here's the reaction for the extraction of iron from its ore, hematite F, E2O3. We can also look at it in terms of electrons. In the oxide, iron exists as its ion Fe3+, and it gains 3 electrons to form iron atoms. Carbon reduction is an effective method of extraction and is standard for iron. It is also relatively cheap as carbon is readily available. However, carbon reduction is effective for extracting metals like iron. It doesn't work for metals that are more reactive than carbon, as carbon cannot displace them from their oxide. These metals form stronger bonds with oxygen, making them difficult to reduce using carbon, which brings us to another method of extraction. For metals more reactive than carbon, an alternative method called electrolysis is used. Electrolysis involves passing an electric current through a compound to break it down into its constituent elements. For example, electrolysis is used to extract aluminium from its ore bauxite as it separates the aluminium metal from oxygen. In upcoming lessons, we will look at electrolysis generally and also examine the specific case of extracting aluminium from bauxite in great detail. While it is an extremely effective method that can be used to extract almost any metal, it's also very expensive as it uses large amounts of electricity, hence why carbon reduction, if it is possible, is preferred. The last category of metals are gold, silver, and platinum. Those three are an exception in the world of metal extraction. They are very unreactive, which means they do not form compounds easily. Because of their low reactivity, those metals are often found in nature in their pure, metallic form and do not need to be extracted from ores through reduction or electrolysis. This shows how the reactivity series is crucial for understanding how different metals can be extracted from their ores. By understanding the limitations of carbon reduction, we can appreciate why alternative methods like electrolysis are necessary for more reactive metals. In today's lesson, we explored the extraction of metals and how the reactivity series guides the choice of extraction method. We explored the carbon reduction method for metals less reactive than carbon, such as zinc, iron, and copper. We then highlighted the limitations of carbon reduction, particularly its ineffectiveness for extracting metals more reactive than carbon, such as aluminum, magnesium, and sodium, and introduced electrolysis as an alternative method for extracting highly reactive metals. We concluded by noting the special case of gold, silver, and platinum, which are often found in their pure form and do not require extraction from ores. This lesson has provided a comprehensive understanding of how the reactivity series is utilized in the context of metal extraction emphasizing the need for different methods based on a metal's reactivity.